Hi, everybody. This is a continuation of lecture 16, Thursday, April 2nd, week 6. That's the only lecture of this week. We met for about 10 minutes in the room, and then there was a fire alarm. So I suggest that you look at the first 10 minutes in the Blackboard recording and then pick up from here. This is how we ended about an hour and a half ago, those 10 minutes. There was a fire alarm. I believe it was a Guzman Gomez type of overfrying issue. I don't know.
DDF f of x of, and I tell you it's of a continuous random variable, PDF little f of x is d dx of f of x. Okay? That's what the CDF is. I take the derivative. All right, so you convert between the two in this way. And that's this equation here. Please not here. No, 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 no. We have stuff to cover. Okay, we'll continue outside. All right. This is not a drill. Come on, come on, come on, come on, come on, come on, come on.
Okay, so we were here understanding that there is a CDF capital F and there's a PDF little f. I just remind you that, or tell you that the density is not necessarily a probability because f of x does not have a probabilistic meaning. So f of x is not the probability of something, little f of x. However, if you multiply little f of x by a small h or a small dh, then that is a probability of having the random variable fall in the neighborhood of x. So whenever you have any function that has non-negativity and is integrable with the integral equaling 1, then it is a valid PDF probability density function. For example, the uniform distribution is one such case. So take f of x, which is 0 everywhere outside of 0, 1, and on the interval 0, 1, it is 1. So if you integrate this from negative infinity to infinity, that's like integrating from 0 to 1, and that integral is obviously 1. Now, you can also go back and get the cumulative distribution function of this. So basically, if we're integrating for x's that are negative, then we're doing from negative infinity to some x negative on 0, and hence we're 0. And then when we continue and add to that integral, the integral from 0 to some capital X of the constant 1, that integral is just x. And finally, when we're continuing to integrate more to the right and moving on x's that are greater than 1, then we're again integrating a 0 again. Right now, once you have this density for any subinterval a, b, which is a subset of 0, 1, if you want to look at this probability, then you can just integrate over the probability, and that's of course b minus a, so the probability is a length. Okay, that's a uniform distribution. Here's an example of a non-uniform density. So again, this is a density function because the integral of the function that is 2x on x being 0 to 1 is just going to be 1. The area of this triangle is 1. And again, if you are doing now the cumulative distribution function, then going for x's that are negative, you're just doing negative infinity to some negative. Well, f of t is just going to be 0 there. And then if you're going to x, which is someplace between 0 and 1, then you have to add to that 0 before the integral of 2x of from 0 to x. And that's going to be the x squared. And finally, onwards from the support, onwards to the right, you're again integrating zeros, and that's why you get this shape. Okay, so again, you can compute probabilities using the CDF in the exact same way. So for this example, for example, this was the CDF, and this is the PDF. So if you're looking for a specific probability, say the probability of being between 0.3 and 0.7, it is the area under the PDF, or alternatively, it would just be the CDF at 0.7 minus the CDF at 0.3. Okay, so a linearly increasing density implies a quadratic increasing CDF. But when you're integrating this thing more and more to the right, after the support is finished, or to the right of it, then you've just got a constant there. Okay, just as an example of a density exceeding 1, and there's many cases, take, for example, a uniform distribution between 0 and a third, then our PDF is going to be 3 because for that integral to be 1 over all of the support of f of x, we need the 3 times a third is 1, right? But of course, 3 is not a probability. That at least gives you a bit more convincing argument that densities are not probabilities, if you'd like. And this is a table that I discussed also in lecture 15 that kind of compares discrete and continuous distributions. Okay, so study this in detail. There's a whole lot of info there, but that's a story. All right, moving on to expectations and moments and other properties. The good news is that we're already experts of these kinds of things when we come to discrete random variables. So continuous random variables are not very different. So first of all, the expectation or the mean is the weighted average of the values that the random variable can take, weighted by the density, if you would like. For discrete random variables, we had a summation over a support. For continuous random variable, we have an integral over the support. Now, hey, you could say the support is not necessarily negative infinity to infinity. That's okay. F of x is going to be 0 outside of areas that are not the support. So you would only integrate on that subset, which can be an interval, a right open interval, or something more complex. Okay, an expectation exists when the integral converges absolutely, and you will see in chapter 6 cases where the expectation does not exist. Okay, in some cases, you'll see that it exists, but the integral diverges, so it's basically infinity. We sometimes write mu for the expectation, sometimes we put a subscript x. Okay, so say if we take a uniform distribution, the expectation is the integral over all of the domain negative infinity to infinity, but the support is 0, 1. So what we're doing is this x, and f of x is this 1, and that's x squared over 2. And substituting the boundaries, you've got a half minus a 0, and that's why you get a half for the mean. Okay, and if you go for this other density, well, let's just think intuitively. If we look at this density that goes like this, we would like the mean to be someplace more here to the right? Because there are more probable values to the right of half. So let's see what that turns out to be. So in this case, it's x times 2 of x. So that's like 2 times the integral of x squared. Okay, and that happens to be at 2/3. You can again do the law of the unconscious statistician, Lotus, and you can take the expectation of a function of a random variable in the same way. So now instead of having little x here, we have h of x. Okay, and most important with that is, for example, if we have the second moment, then you've got an integral of x squared. So the second moment of this random variable happens to be a half. Okay, and in the same way, just like we had for discrete random variables, you've got the kth moments and you've got the kth central moment as well. Most importantly, the variance is the second central moment defined really in an analogous way to the discrete case, and that's this integral. And the same formula for the variance is saying that it's the second moment minus the first moment squared will still hold. So say if you want the variance of the uniform, then you can actually compute this like this from first principles and see that the variance of a uniform random variable, uniform 0, 1, is 1 on 12. So properties of expectations of variance, the same properties we had in discrete random variables. So expectation of an affine combination is an affine combination with expectation. The expectation of a sum of functions of the random variable is the expectation of the sum of the functions. The variance of the affine combination is not troubled one bit by this shift b, but a goes outside a squared, and the proof is analogous, or the derivation is analogous to the continuous case, in the continuous case to the discrete case. And finally, the variance of x's is the second moment minus the first moment squared. So if you're talking about mean zero random variables, the variance is the second moment. Okay, and the proofs follow in the same possible way, in the same way. So here is like you could again see the variance of a uniform. For example, the second moment happens to be a third, and then you got a third minus the half, which is a mean squared. That happens to be a 12th. Okay, and here's another example. So let's say if we want now what we call a continuous uniform distribution on AB. So in this case, we define the density not to be a density of height 1, but it's a density of a height which is actually 1 minus B minus A, because this way, if you compute the area of this rectangle, it's going to be exactly 1. That here is this rectangle. Okay. And it's a good exercise to get the CDF of this uniform exactly as it is. So here I'll try to annotate on the screen. So if we have this is the x-axis and this is A and this is B, the CDF is going to be increasing at such a slope, and that slope is 1 on B minus A, and this is the point 0. This is the 1. This is probability 1. That's again the CDF. Okay. So again, if the CDF to obtain the expression for the CDF, and the CDF is defined for every possible real valued x, we integrate the density. So again, I'll also draw the density here. The density is just going to be this kind of height of 1 on 1 minus B minus A. That's the density. So when we're integrating up to the point x, when x is less than, this is A and this is B. This is A and this is B. When we integrating to the point x and x is less than A, we're integrating over 0, that's nothing. But then once we start to move for x being greater or equal than A, then we're integrating a constant, and that integration of the constant rises like this. And then when we continue moving to the right, we're not integrating anything more than 0, so that's why we're fixed at 1. Notice that you put this upper boundary here and you get B minus A, B minus A. Okay, so that's that. And using this density, you can, from first principles, and I recommend doing this by first principles, I mean just doing the integral, you can see that the mean is the midpoint, A plus B over 2, and the variance is B minus A, meaning the length of the support, B minus A squared over 2, or the standard deviation is B minus A over root 12. Of course, you can also get this by just considering this transformation, because you can always move from a uniform 0, 1 to a uniform AB. Try to think how to do that. So I'll just say that there are other descriptors. For example, the skewness is determined by the third central moment normalized by the standard deviation cubed, and that is some measure of asymmetry of a distribution. So the skewness is going to be positive if you're right skewed, negative if you're left skewed, and 0 if you're a symmetric distribution. Try to see as an exercise that if you take any symmetric PDF, so the PDF is symmetric around mu, okay, so that means that the PDF reflected around mu is the same, that the skewness is going to be 0. Another descriptor is called a kurtosis. Now, this is a numerical value, doesn't tell you a whole lot, but for normal distributions, the kurtosis is 3. So sometimes you take this kurtosis, which is a fourth central moment normalized by sigma by the variance squared, or the standard deviation to the fourth power, and you then subtract it from the 3, and then you kind of see if you're more kurtosis-y than the normal distribution or less. Kurtosis is some sort of measure of how much energy or how much mass you have in the tails. Other things of interest are the quantiles, for example, the median, and I'm not talking about the median of data, I'm talking about the median of the probability distribution, is the value m such that the CDF of m is half. So it's that value where half of the mass is to the left of it. Okay, and it's a special case of the quantile. So the qth quantile is that value xq such that f of xq equals q. Okay, so these are all nice and good. They give for good exam questions or items, etc. when you get a distribution. And here again, we're stuck on this kind of very special distribution 2x on 0, 1, and we can do the third moment and the fourth moment, and we can even do the third central moment as a function of the third moment and the second moment and the first moment, right? So you can open up these brackets just by binomial expansion and kind of get this expression. And hence, you can actually get an expression for the skewness of this distribution. Okay, and similarly, you can even get the kurtosis. So a lot of computation is to be had just from kind of simple things in the Go, and here's also quantiles. Okay, let's get to the most important thing that you'll ever see ever in your life. No, maybe, I don't know, but maybe not the most exciting, but a big deal, the normal distribution. So the normal or Gaussian distribution is the probability distribution that appears everywhere in nature because of this thing called the central limit theorem, which you'll visit with Kazu in chapter 10. It's a probability density function that has this form, and it's defined for any value x. So the support is all the real values. So it has two parameters, mu and sigma, which will happen to be the standard deviation, the mean and the standard deviation, respectively. And what we're doing is the exponent of minus half of x minus mu divided by sigma squared, and there's also this normalizing constant here. And we write it like this. Now, just a warning, in software packages, sometimes the second argument is a standard deviation, and it can also be in notes and notation. So when you put normal something, something, make sure that it's very clear if that something on the right is the standard deviation or the variance, okay? So there's no ambiguity there. Of course, if the standard deviation is 1, the variance is 1. Otherwise, they're not equal. A standard normal has mu 0 and sigma 1 and has this much simpler form, and that's what it looks like, e minus x squared over 2. And it turns out that for this thing to integrate to be 1 for e minus x squared over 2, the normal, that integral, well, that integral of this thing that I'm highlighting from negative infinity to infinity is square root of 2 pi. And this is why we normalize by 1 on square root of 2 pi. Okay, now to actually see that this integral of square root of 2 pi is not the easiest thing in the world, certainly not the most trivial thing in the world. Okay, and what you can do is you can actually take this integral and multiply it by itself, and then use Fubini's theorem, or just convert this into, basically, from an informal perspective, just take this integral and put it inside and convert it into a double integral. So we're doing now a double integral on dx dy. And you'll see more things like this when we speak about moments in general for multidimensional distributions in chapter 7, chapter 8, etc. Now, if you take this double integral and convert it to polar coordinates, then you get, now you're integrating dr d theta, and r will go from 0 to 2 pi, and sorry, theta will go 0 to 2 pi, and r will go 0 to infinity. And this integral, you can actually solve this. You actually get an expression for this integral. And then you see that it just happens to be 2 pi. So if I squared equals 2 pi, I is root 2 pi. And that's how you get that normalizing constant. I've gone quickly over this calculation. This is going to appear again when you speak about transformations of vector random variables, and in particular when you go, say, from Cartesian coordinates to polar coordinates of bivariate random variables. And this type of computation will again be relevant then. Okay, now a thing about the normal distribution is, even though it's so popular, there is no explicit formula for this, for the CDF. This is a CDF of the normal, and there's no explicit formula for it. So then we denote it by phi, and this is how we have these common normal probability tables. So normal probability tables, this is, they tabulate the standard normal distribution. You could, if we might give you normal probability tables in the exam, if needed. Okay, so, and maybe in the next lecture, lecture 17, I'll quickly show you a table. But in a computational setting, You can do, for example, SciPy stats, the norm, and then the norm dot CDF is going to give you the standard normal CDF values. Okay. Now, for a normal random variable that's distributed with mu and sigma squared, if you then do the following transformation to it, you subtract mu and divide by sigma, or alternatively, you do the affine transformation of multiplying by 1 on sigma and adding minus mu divided by sigma, then what you get is a 0, 1 standard normal random variable. So let's look at the proof, and this is a special case of a transformation of random variables, which we'll do more in Unit 6. So let's say that X is distributed normal mu sigma squared, and now Z is this standardized form of it, okay? What is the probability that Z is less than or equal than Z? Well, that's a probability that X minus mu over sigma is less than Z, and you can multiply by sigma. Sigma is non-negative, so it doesn't change the inequality. And then you can add mu. So that's this probability of X. And that is then the CDF of the normal with mean mu and variance sigma squared up to the point mu plus sigma Z. Okay. And you can now go and you can move this back to be just by a change of variables, this change of variables in the CDF, just to be the standard normal the integral over the standard normal PDF, so namely the normal CDF at the point Z, and that is phi of Z. Okay. So this kind of change of variables, this one, y equals x minus mu over sigma, in this integral converts us from a CDF of the random variable x at the point mu plus sigma z to the standard normal CDF. Okay, so this is called standardization, and this is why we don't have many normal probability tables. If you're using a probability table, you can always speak about normal in the standardized form. So you can always take a general normal with X like that and speak about it. If you want to look at the CDF at the point X, that's like looking at the standard normal CDF at X minus mu over sigma. Okay, that's it. That's what we have here. And then we have mu plus, yeah, so, and that's that. Now, the mean over the normal happens to be the parameter mu, so it's centrality parameter, and it's symmetric about the mean. And the variance happens to be sigma squared. And these are actually computations so you can carry out. So you can compute the second moment. So this is z squared times the density, and we're integrating that. And if you do this integration, in this case, even though this integral on its own right, you cannot get an explicit form, but if you're doing integration by parts, then you will get that this thing equals 1. Okay, now the second moment is 1, and the first moment is 0. 1 minus 0 squared is 1, and hence you see that the variance is 1. That's kind of for a standard normal. And then you can use the transformation of the variance from a standard normal to an arbitrary normal with variance sigma squared using this rule of the variance. Okay, you can do the same or here you can do the mean. So it actually takes a bit of work, and I recommend going through this work that when you're given a normal with a parameter mu and a parameter sigma squared, it's actually the mean of that normal is mu and the variance is sigma squared. Okay, now the probabilities of being 1 standard deviation away, 2 standard deviation away, 3 standard deviation away from normal are kind of generally known numbers, roughly at 68%, at 95% roughly, and at about at 99.7%. Okay, and the normal is symmetric, linear transformations of normal. And when you compute a probability like this for an arbitrary normal, you can again standardize and do the probability with standard normals. So that's it for the normal distribution. This is stuff you often, if you would have seen this in a different course, then that's a bit of a review, but maybe in the previous course you didn't go through this computation per se, and maybe you didn't go through the fact that the y is the normalizing constant of the normal, 1 on square root 2 pi, okay, for the standard normal. But otherwise, I hope this would have been reviewed for many of you. If it wasn't a review, then just take a bit more time to study this thing. So in the next lecture, we'll pick up and we'll finish chapter 5 by looking at the exponential distribution and then also the gamma distribution and the beta distribution. Okay, wishing everybody a good long break. Please use a break to also catch up on the study material, the reading material, the practicals, and the assignments. There's obviously a lot of material in this course, and hope everybody has a good break. Bye bye.